Hello, everyone. Welcome to this lecture series, which is designed to investigate complex systems which generate a lot of observables, a lot of big data, huge data. And for a major part of this lecture series, we will be using as our reference this textbook, Methods and Applications of White Noise Analysis in Interdisciplinary Sciences, which you can just get, for example, from Amazon or World Scientific. So let's start with this observation that evolving technology has allowed observations and data gathering because technologies nowadays are faster, bigger, more memory, it's finer, and it's easier. So this rapid and exponential increase in data has to be, all this data have to be interpreted and to see what is the underlying story behind this big data. Now, uh, so big data analytics or big data analysis is actually a keyword in the 21st century. And just to give you a flavor, for example, the DNA instructions passed from parent to child has roughly around 3.1 billion letters. And there's also a lot of data in network traffic over time. You can also have, as an example, the Dow Jones daily return for the past 50 years. There are thousands of amino acid sequences in the protein data bank. And as an example, there are also hundreds of recorded typhoons or cyclones throughout history. And if you want to study the brain, there are 10 to the power 11 neurons and 10 to the power 14 synapses, which connect all these neurons in the normal human brain. So a huge amount of data, and we would like to know how to handle them mathematically, computationally, and all that stuff. So there are many definitions of big data. You can look at it, define it in whichever way, but some textbooks or references would say that big data refers to high in volume, velocity, and variety of generation of this data. They are quite exhaustive in scope. They are also fine-grained in time, in temporal or spatial resolution, and inherently relational, especially if the data points would have history or correlations within themselves. So this huge amount of data might be generated using everyday life, Twitter, gathered by sensors, scientific experiments in space, videos, or this could be data repositories made public by governments and corporations. Now let's look at a bit of history. Let me quote from this reference that as recently as the year 2000, only about 1/4 of all the world's stored information was digital. The rest was preserved on paper, film, and other analog media. But because the amount of digital data expands so quickly, it's doubling around every 3 years. Today, less than 2% of all stored information is non-digital. Of course, this comment was made in way back in 2013, so it would be a little bit different today. Also, based on 2013 comments, if all this information were placed on CDs, of course we don't have CDs anymore, we use DVDs or USBs. If all this information were placed on CDs and they were stacked up, the CDs would form 5 separate piles that would all reach to the moon. So this is just an illustration of the amount of data that we have available, especially in the internet. As we tap ever more data to understand events and make decisions, we are likely to discover that many aspects of life are probabilistic rather than certain. That's where the stochastic processes would come in. A bit of history also, Google Trends reveals that in 2007, almost nobody was searching the web for the words big data. Only towards the very end of 2010 did the term begin to register, just ahead of an explosion of interest from 2011 up to today. And Google Trends also shows that in mid 2013, searches for the data scientist surpassed those for statistician for the first time. So this is just to put things in perspective historically and in the context of today's world. So data analytics is, again, a big word nowadays. But how does one handle a huge number of seemingly random data points, seemingly random observables? Well, the business world, corporations, and all these agencies have a way of visualizing all this data. So for example, they can visualize big data to guide their business decisions, for example, using connectivity or histograms or a time series and many other computational representations of big data. Let's go through this quickly. An example of, for example, starting with connectivity. So connectivity, what do we mean? This is a picture of several data points. There are a lot of nodes, and each node is connected to neighboring nodes. And the bigger the dot, that means the bigger is its connection with its neighbors. Now, to put it in a more true-to-life context, let's look at this figure, for example. It says big data telling the story of falling oil prices. So this was taken from the reference below, and of course, prominent here is the former President Barack Obama. And the bigger the point means that the bigger are its connections with everybody else. So it tells a story. So visualizing big data in terms of connectivity tells a story and can guide a lot of people. Now, another way of telling the story of big data is through histograms or frequency distributions. This is very common, especially for teachers when they plot the distribution of grades of students. But in this particular example of a work done in 2013, this makes use of Twitter. So they counted the number of characters used when sending messages. Horizontal line would be the message length and the probability. And of course, the number of characters used would change from 2009 up to all the way to 2012, and especially nowadays. So, but this is an example of a histogram. Another way of visualizing big data is through a time series, and this is a classic example. This is a time series covering several years of the depth of the Nile River. So it fluctuates. The depth of the Nile River fluctuates, and in fact, this was studied by Hearst way back, and it was the basis of this study by Professor Hearst, which later on led to fractional Brownian motion. That means this type of fluctuation has memory, and we will deal with a lot of memory behavior in our story of stochastic processes. So this is time series. Of course, a lot of people would be interested in revenue and forecast of revenue, what happened today and in the past, and what should we do business-wise, what is our forecast. So that's also a time series, and so you have to visualize all this big data. You can look at, for example, the Philippine stock market. Of course, if there's something like COVID-19, nobody could really predict what would happen, but at least in normal times, you can have some sort of prediction if you have some sort of visualization in terms of connectivity, time series, or histograms. How about natural phenomena like typhoons? Let's for example, let's look at this example of Sendong, or internationally known as Wachi. This is the path of Sendong, which crosses through the Philippines. And how do I investigate this problem? There are a lot of ways of looking at this problem, but one way is, suppose you have this data. Normally this data is open access. This is going north, and this is the time, and the red line would be the actual positions of the typhoon, and we can put a blue line, which is a linear fit of the fluctuating positions of the typhoon. Now, what we are going to do next is to create more fluctuations from this graph. That means, suppose I look at the actual point at around maybe 110 hours and subtract the actual position from this linear fit, okay? Then I would generate a number. Then I'll do that with all the actual positions subtracted from the linear fit. And those numbers that I generate would be fluctuations from the linear fit. So fluctuations from the linear fit would look like this. And you can actually analyze this, and we have analyzed this using our stochastic process approach. And but this is just an example of a phenomena. So in real world, there are really a lot of fluctuations of observables from different sources. And we would like to know what is the story behind these fluctuations, what is the story behind the numbers. Now, so huge amount of data, which are open access, they need to be analyzed for patterns, universal features, scaling phenomena. Of course, you can do visualizations. But as physicists, as mathematicians, as scientists, we would like to look at it from a different point of view. We would like to know the mathematical structure behind these big numbers. And normally, as a guide, we learn from the history of science that nature is very economical in principle, but maybe complicated in structures. But that's something we have to put at the back of our mind when dealing with these big numbers. So historically, these complex systems involve many parts. So we have to study how parts of system give rise to the collective behavior, which can be observed macroscopically. And you can look at examples of social systems, out of people, the brain formed out of neurons, or you can look at the molecules formed out of atoms, the weather formed out of airflows, are all examples of complex systems. And the field of complex systems cuts across all traditional disciplines. It's interdisciplinary. It could cover engineering, management, math, computational, computer science, and medicine, and all over. Now, physics has been dealing with complex systems since almost like time immemorial. That's how statistical mechanics or statistical physics was created. And for example, they were looking at Avogadro's number, which is 10 to the power 23 molecules in a container. How do you study this 10 to the power 23 molecules in a container? Do you look at individual molecules, or you apply something else? And that's how statistical mechanics or statistical physics was born at around 1900s. The goal of statistical mechanics is the understanding and prediction of macroscopic phenomena and the calculation of macroscopic properties such as, in this case, pressure, volume, temperature, as a result of this huge number of molecules inside the container, as an outcome of the properties of individual molecules which make up the system. So this is an approach of how to deal with big numbers. And statistical physics has been doing that for a long, long time. And in statistical physics, you have a physical ensemble, which are the embodiment or idealization, contracted picture of macroscopic systems. They have a huge amount of samples, an ensemble, and the natural mathematical setting for treating such ensemble is the theory of stochastic processes. So here we are. We're now in this lecture series would cover stochastic processes, Gaussian and non-Gaussian. So the question is, can we really go beyond big data visualizations? What people are very familiar with, what the corporation or the business world is very familiar with. They input data and they have these visualizations. But we would like to know what's the story behind these big numbers mathematically. What is the mathematical structure? And can we improve predictions, making use of the mathematical structure that we can see? So we ask ourselves the question, is there a theory or stochastic process behind these big numbers? And if there is, if yes, then what is it? So I'll end here. In the next lecture, we'll talk more about mathematics, but first we will lay down the foundations of this. So thank you very much. This my last slide for lecture 1.